Alright, hey guys, welcome back. So here in this video, we are going to be going over this problem. It's a conservation of energy problem that includes both gravitational and spring potential energy and thermal energy lost due to kinetic friction. So on this page, I have it all worked out, or we have the problem, and then we're going to scroll over to see what this actually looks like. So a 4 kilogram block is hanging by a light string that passes over a massless, frictionless pulley, and then is connected to a 6 kilogram block that rests on the shelf. The coefficient of friction, kinetic friction, is 0.2. The 6 kilogram block is pushed against a spring, compressing it 30 centimeters. The spring has a force constant of 180 newtons per meter. And what we're looking here is to find the speed of the blocks after they have moved 4 centimeters. So there's a lot going on here with any good physics problem. First place we want to start is just drawing a diagram. So that is what I have here for us, is I've put all that information into a kind of picture. So we have our 4 kilogram weight is hanging, the 6 kilogram block is on the shelf, it is compressed the spring, it's pushed up against the spring. There is a coefficient of friction here between the block and the shelf that it's on. And what we're going to do is both of these are going to move a distance of 4 centimeters. So I could have I didn't put that up here, but I could have, if I wanted to, also done this to say that it's also going to move 0.4 meters. So this is what we are looking at here. So with any energy problem, we want to start with our basic formula that work external is equal to our change in mechanical energy minus our work non-conservative. So pretty much what that is saying is that if we're adding any work into the system, so if we're adding any energy into the system, that energy is then going to be converted into potential or kinetic, or it's going to be converted into thermal due to a non-conservative force. And so we look at the system and we think about the work external. Typically, our work external, when we're talking about that, we're talking about a force applied. Here, the only forces that we see are part of the system. There's the tension that is holding our blocks together. There's the friction between the block and the shelf. There is the spring force, but all of these are part of the overall system that we're looking at. So when you look at this, we're not actually going to have a work external. What that means for our equation then is that our change in EMEC has to be equal to our work non-conservative. So these are the things that I want to be looking for as I try to solve out this problem. Well, if we talk about our change in EMEC, it's really important to remember that a delta is our final minus our initial. So we need to figure out what is our EMEC at the final and our EMEC at the initial. So the different things that are going to give us mechanical energy here, there's potential of the spring, there's gravitational potential, and there is kinetic. Those are the three things that are going to make up our mechanical energy. Well, if we think about it, the final, I can't obviously make my blocks move, that would be really nice, but at our final, our blocks have moved the 4 centimeters away. Because the block is no longer engaged with the spring, the potential energy of the spring isn't going to affect us here. So we're not going to have any potential of the spring at the final because our block is no longer engaged with the spring, so that no longer exists for our problem. When we get to the gravitational, however, the gravitational potential energy is coming from this guy. This one up here is moving, so his vertical distance is not changing, just his horizontal distance, so he's not having a change in gravitational. This one is moving down, though. It's moving down 4 centimeters, 40 centimeters to 0.4 meters, so it is losing potential energy. So we're going to represent that as, I need to label my block so we know which one is which. Let's label the one at the top. We're going to label this one M1. I'm going to label this one M2, just so we can keep it together over here. So my gravitational is going to be M2G, and then the distance, it's going down. So this distance is 4 meters, so I'm actually going to give that a negative D. So because it is going down the 0.4 meters. Our kinetic energy then is 1/2 m. Well, here, if we're looking at our system, the mass is made up of both of the blocks. So when we do the mass here, we're actually going to be doing m1 plus m2. And then the v squared is what we're trying to find. We're trying to find that speed at the end. So my total final would be 1/2 m1 plus m2 velocity squared minus m2gd. And so that minus came from the negative on the d. I just went ahead and moved it up to the front. So that is our final mechanical energy of the system. The question is then, what is our initial mechanical energy of the system? Once again, it's going to be made up of spring potential, gravitational potential, and kinetic. So if we start at the bottom here, if we start at the kinetic, we know at the very beginning of the system, the blocks are not moving. So it's going to be 1/2 m. I'm going to use a big M because we know we're talking about both of them. 0 squared. So that actually ends up canceling out. We don't have it. Our gravitational, I made this spot right here, y equals 0. That is why this became a -4, because I said we're starting at y equals 0. By doing that, we made it really easy that it's going to cancel out here. So I get m2g times 0. That one also cancels out. So talking about potential of the spring, then we come up here and we see, hey, the spring was actually compressed 0.3 meters. So we do have potential energy due to the spring to start us off. So 1/2 k x squared. So our total energy to start off with is 1/2 k x squared. The last one we have to talk about then is, I'm trying to figure out what color I want. The work non-conservative. That's the last bit that we need here. Well, we know that when we're solving for work, if we can, we know that work is force times the distance. We know the work total can be the change in kinetic energy, but here we're really just looking for the work as a non-conservative force. That is what we're looking for here. So we're just going to do work as force times distance. Our non-conservative force then would be the force of friction. The force of friction, we know is going to be mu, and then it's going to be mu n, but in this case, our n is going to be m2g, and that's because the block that's actually going across the friction, this friction full surface, is this block right up here, so m1, and we know that if we were to draw a free body diagram for him, his force normal would be equal to his force of gravity because there is no angle here. They are perfectly opposite of each other. I guess it helps if I actually remember which one is which. So we said that was m1g. So we can come over here and say that our force of friction is going to be mu m1g. And then the distance, we got to think about this in terms of what we know about work. The block is moving 4 to the right. So that is a +4. It is going 4 to the right. But our force of friction is going in the opposite direction, so therefore it's going to be a -0.4. So our distance, once again, kind of like we did with the gravitational, is going to be our -d, which means that our work, non-conservative, is equal to mu negative mu m1 gd. So here we have all of these different parts, and based on this statement up here, we can set some things equal to each other now. So we are going to say our final mechanical energy, so 1/2 m1 plus m2 v squared minus m2 gd, so that's our final, minus our initial 1/2 k x squared is equal to our work non-conservative, which is negative mu m1 gravity distance. So putting these things into this formula, that our change in mechanical energy has to be equal to our work non-conservative. And here negatives do matter, so once again, we're losing the energy. Another way to think about this, because I know, or no, we're going to finish the problem. Then we'll talk about another way to look at it. So here we can just go ahead and start plugging numbers in once we get here. So we're going to have 1/2, N1 and N2 is 10, V squared minus the mass 2 is 4, gravity is 9.81, that distance 0.4, minus 1/2, 180, it was compressed 30 centimeters, is equal to negative 0.2. The mass of that one is 6, gravity is still 9.81, and that distance is still 4. We go ahead, put these values, evaluate some of these values. We're going to get 5v squared minus 15.696 minus 8.1 equals negative 4.7088. We solve this all out and we get that our velocity is 1.95 meters per second. So that is just solving the problem out the first way through. Now, the majority of people's mistake on this problem came from the work non-conservative. Majority of people just said that the work non-conservative was a positive quantity. And if you did that as a positive quantity, if you took all these out, you ended up getting the velocity was approximately 2.34 meters per second. You can see, honestly, they're not too far off, but they are off. They are different. And so we have to think about this in terms of what we know about conservation of energy and just what's going on here. So there was an original amount of energy, which is 1/2 kx squared, and we can even figure that out. We know that that quantity, we found it was 8.1 joules, and I found that from here, just following my math. So there was originally 8.1 joules here. As we talk about this, we have to figure out what was all going on. Let me try this again. I'm not explaining this well. We started off with this 8.1 joules of energy in the system. By the end, the entire system still has to have 8.1 joules. And if we think about it, we know that if we are losing, we are obviously losing mechanical energy to thermal. So the mechanical energy here is going to be less than this. So any number less than this, we could even just say it was 5 minus 8.1, because we're doing final minus initial, is going to give me a negative number. That would be, what, negative 2.9. But because we are losing some of our energy into thermal, the difference here, the change in mechanical energy, had to be a negative number. That means that the final mechanical energy is less than the original mechanical energy. That's what a negative change in mechanical energy means. Because we were losing mechanical energy, the change had to be negative. That means that when we are doing this statement, if we just think about that in general, we had to be setting the change in mechanical energy set equal to a negative quantity. We had to put the change in mechanical energy set equal to a negative quantity. This negative up here is here because work non-conservative is typically you have something going in the opposite direction. Most often what we get is that our work external is equal to our change in EMEC minus the negative work of minus the work non-conservative, but the work non-conservative tends to be a negative number. So we're saying the change in mechanical energy plus the energy that is lost is equal to the work that is put into the system. Here, no work was put into the system. So the work non-conservative was simply equal to what was lost. So just really trying to help you guys out there with the negatives. You saw me go through the whole problem, how I figured out why there should be a negative here. But also, you just have to think about what's going on in the problem. And once again, the way that I did that is I knew that we were losing EMEC to ethermal. We know that our energy is being transferred from mechanical to thermal. So because of that, my change in EMEC had to be a negative number. Therefore, when I did delta EMEC equals work non-conservative, it made sense for this to be a negative quantity. And there we have it. It's a negative quantity, and it was a negative because it was going in the opposite direction of the movement. The work, the non-conservative force, was opposing the movement, and that is why it was a negative quantity. So there you have it. This is a conservation of energy problem that includes pretty much as much as we can see. At spring force, it had a gravitational or spring energy, gravitational energy, and kinetic due to moving, as well as kinetic friction in this portion.